I'm going to talk about a joint project with my former advisor, Zoltán Vucelic, and I'm going to talk about tent maps. So I'm pretty sure that the majority heard of the classic tent map, which is just a very simple system. It has just one parameter, the slope of the tent. It lives in the unit square. And the entropy of the classic tent map is just the logarithm of the slope. And you can only move the top of the tent vertically, and as you go up, the entropy will go up as well. So in our system, we have two parameters. The top of the tent can be anywhere in the unit square. And we are interested in the question that what will happen if you shift the top of the tent horizontally, how will the topological entropy behave? So that's the main question. And in order to prove that, we will investigate other properties. Okay, so this is how it looks like for some parameters. It becomes very spiky, very, very fast. And although it becomes very spiky, it's not true everywhere. This is the only parameter range where the dynamics is actually interesting, because if we are below the diagonal, then the 0 point is an attracting fixed point, so it will be just flat. And if we are below the other diagonal, then there will be another attracting fixed point, so it's just boring. But if we are in the yellow triangle, then we have two repelling fixed points, and those will cause the interesting dynamics later on. Okay, so this morning we heard many definitions of the topological entropy, and those are quite good. But I will use another one introduced by Mizerowicz. So we can count the spikes. We call them basically lap number. That will be the Cn. So if you take a monotone partition of the nth iteration, then the minimum of the cardinality of this kind of partitions will be the lap number. And the entropy can be just simply the logarithm of this lap number divided by n, and we take the limit. And that's it. That when I will use topological entropy, then I will mean that, and I will denote it by h alpha beta. Okay, so the first tool we use is the Kneading sequence, the Kneading theory. We just take the itinerary of the extremum, the alpha, and if the nth iteration is smaller than alpha, then we simply put an L, as it's the left side of the tent, it goes to the left side. If it's bigger, we put an R, as it goes to the right side. And if it comes back to alpha, then we put a C. So here we will get some sequences, and there is an ordering on these sequences. It's simply L is the smallest, R is the biggest. And if we have two sequences, we can compare them. So let's take the part till they equal, for example, till the jth letter, and then compare the next one. And we have to calculate how many R's are before in the sequence, and if this number is even, then it will preserve the ordering, and if it's odd, it will reverse. It was very long to explain, but it's very easy. So for example, there is RLLC and RLRRC. They are the same in the first two letters, and then in the third one is L and R, and since we had only one R before, it will reverse the order. L will be bigger than R, so RLLC is bigger than RLRRC. Okay, and why is this good for us? We have this known thing that if we have two different tens denoted, the top of them denoted X and Y, if X strictly smaller than Y, then the Kneading sequences has to be smaller or equal, so they can be equal. But not the other way around. If we have two strictly different Kneading sequences, then the points have to be strictly different as well. And here's a theorem we get. Mizurewicz and Vishnyasny has some similar systems. So our theorem comes from there. I denote the Kneading sequences of the upper triangle with that Gothic M. And if we take a Kneading sequence from this Gothic M, then there will exist an alpha 1 and alpha 2 and a continuous function psi m, which will go from the interval alpha 1, alpha 2 to the upper triangle, and k alpha beta equals this m Kneading sequence if and only if beta equals this psi m alpha. What does this mean? Yes. I will explain. So this is just look at the nice picture. So here is it, for example. This is the Kneading sequence RLR infinite. And if you just take one point from the curve.
The curve that fixes the Kneading sequence.
Yes, that fixes the Kneading sequence. And since the itinerary of the top is the same, all of these tens. So just imagine that you can put infinitely many tens on this. So the Kneading sequences are the same, and therefore the entropy will be the same as well. And these curves fill up the upper triangle. And this is also very interesting, this special curve, this RLR infinite, because it divides the upper triangle into two halves, and above this curve, all the tens are topologically mixing, and below they aren't. So unfortunately, I don't have.
Wait, this is a specific choice of
yes.
For every hour? I don't understand. You have a variation, or that is a particular curve?
This is so. This is a particular curve, but I will show you.
But what makes that this particular curve special?
Yeah, I actually don't have time for that, so maybe I shouldn't.
Because you said below and above.
Yes.
That's what characterizes this curve.
Yes.
They're mixing above and not mixing below.
Yes, and it's actually this is special because on this curve they are topologically transitive, and above it's mixing, and below it's like nothing of those.
Not transitive.
No.
That's a theory.
Yeah.
Oh, that's so obvious.
No, it's not obvious. It's not obvious. And this is how they look like. So if you plot it by MATLAB or whatever, just the first few letters of the sequence, then you get stripes. And you can see it only if you add one more letter, you will have much more stripes. No. It's just that you can't put like infinitely many in the computer, so you just cut it. You just cut. Yes. But they are curves. There will be another picture later when you can actually see curves. So the thing is, so these are the psi m's for different Kneading sequences, and what we want to prove, and we almost proved or basically proved, it's like that they are strictly monotone decreasing. Because if they are strictly monotone decreasing, then if you imagine this vertical line for the classical ten map, as you go up, the entropy is going up as well. And you can correspond it to the fix horizontal line. And if the curves are strictly monotone decreasing, then if you go up on this vertical line, that will correspond to a curve further away on the horizontal line. And in order to do that, we will use other tools. For example, this auxiliary function theta. So this is utterly disgusting, but good news, you don't even need to look at it, because here is it. Much better, right? So if you have an arbitrary sequence there, R, L, L, R, R, and so on, and there is the number of L's, number of R's, and so on, then you will get this kind of exponential series, which has only two terms, alpha minus 1 over beta, and alpha over beta. And it's basically the numbers will show up. So alpha minus 1 over beta will always have just the H1, H2, and so on. Sorry, the sum of them, and alpha over beta is the same. So you will just add up the numbers, and this is how you will get the terms. So it's ugly, but usually one can handle it. Why is it interesting? It's interesting because the zero levels of this theta contains the psi m. What does it mean? Let me show this first. So these are two different leading sequence and the levels of theta m, and where the yellow and the green meets, those are the zero levels. As I said, we are only interested in this upper triangle, so this is, for example, not too interesting that we have a zero level here as well.
I don't understand the picture, how it relates to the leading sequence. This is the parameter space.
Yes.
So you fix a point there, and that gives you a leading sequence.
Yes.
And so what are these colors?
Okay, so you rather fix a kneading sequence first, which is not the same, almost the same, but not the same. So you just take an arbitrary kneading sequence, and that will generate, this series. And you can put alpha and beta in it. And if you put the alpha and beta, which corresponds to this m, then it will give you 0, but not only for those. That's the bad news.
Corresponding in the ones that have that leading sequence.
Yes, but sometimes there will, so let me show again. So here, as you can see, here is a zero level. This is a very nice curve, but here is another one. And this is only one theta. So not only this will satisfy the equation, but another one as well. Here is the theorem, actually. So there exists an m where we know this theta m alpha beta is 0, but the kneading sequence is not only the original, but another one, a very different one. So this is a bit sad, but not too sad, because well, yeah, I mean, besides that it's pretty, I don't know, because the series is very ugly. It's just a tool we use. I would be glad to introduce some very deep meaning of it, but it's literally an auxiliary function. It just helps us to deal with the isentropes, with the curves, with the original curves. So the main point is that the zero levels of these contains our original curves. That's what we need here, because we want to prove that those curves, the original psi m, are strictly monotone decreasing. So the thing is that if we can express, maybe it's comes here? No, not here. Let me go further a little bit here. So we can express the psi prime m, so the derivative, with the help of the auxiliary function. And it is usually, it's ugly again, but since our series is like kind of an exponential series, then it will converge fast enough, except when we are in the corners, because if we are in the corners, then the terms of the series are really close to 1, so it will become very, very slow. So we have problems there, and this is exactly why I'm going to introduce another thing, the Lyapunov exponent, because we will connect the psi-m's with that. So here is the Lyapunov exponent, very, very simple in our case, because we have only two slopes, beta over alpha and beta over 1 minus alpha. So this expression is going to simplify into this gamma times log beta over alpha and 1 minus gamma times log beta over 1 minus alpha, the logarithm of the two slopes. And what is gamma, suitable gamma? It is basically the average time what the tent spend on the left side and on the right side. This comes from Birkhoff's theorem. Basically, so if the formula of the Lyapunov exponent, you just convert it into a Birkhoff ergodic theorem, then you will get this. But the important thing that one can express gamma with the help of the derivative of psi m, with the help of the Isentropes. Why is it nice? It's nice because in cases where we can calculate the psi prime m easily, that means that we can have the Lyapunov exponent very easily as well. But in the times, in the corners, when we cannot really calculate the psi prime m, we can calculate the Lyapunov exponent and then get the derivative. So this can work both ways, which is not bad. Here is it, yeah. What I just said like 1 minute ago. And what is the claim here is this. So that this is the Lyapunov exponent we have. This is the suitable gamma expressed by the derivative of the isentrope. And what's more, unfortunately, I don't really have time to talk about this, but gamma is also mu 0 alpha, where mu is the absolutely continuous invariant measure. So there are a lot of nice connection actually between the entropy, the Lyapunov exponent, and the invariant measure here. And if I had like double of the time what I have now, I would have talked about the invariant measures as well, but I didn't. So the only thing, I still have another nice picture.
Sorry, the main theorem?
But the main theorem is this, but
The purpose of the main theorem is what?
The purpose is that we have a lot of ways and connections between these three main things, the entropy, the Lyapunov exponent, and the invariant measure. And so we can calculate one of them in some cases, we can calculate another in other cases, we can calculate the third again in other cases. So that means that we can calculate all of them, basically every cases. Yeah, so the last thing to remain, it's another nice picture. So this is when we take like 5,000 long sequence, and then you can see that we actually have, like these are almost curves, and this is a tangent calculated from the Lyapunov exponent in this case, and it fits really well. Yep, so I think that was it. So thanks again.